Welcome to this lesson on constructing subsets. Today we're going to break down the famous 2 to the n formula. Instead of just handing you a rule to memorize, we're going to build the proof together using a simple visual binary method. Let's look at the core question. Suppose we're given a simple set with exactly 3 elements. S equals A, B, C. This brings up 2 big questions. First, exactly how many different subsets can we form from this? Second, how do we systematically construct them without guessing? Guessing leads to missing pieces. So instead of memorizing a formula, let's build the subsets from scratch to prove it. Here's our proof by construction. Think of making a subset like walking down a line holding an empty bag. To build a subset, we must look at every single element in our original set and make exactly one decision. Do we include it in our new subset? We look at element A, we choose in or out, giving us 2 choices. We move to element B and make the exact same 2 choices. Finally, we look at element C, and again we have 2 choices. Every path we take creates a unique subset. This branching logic brings us right to proving the 2 to the n formula. By the fundamental principle of counting in mathematics, we multiply the independent choices together to find the total number of possible combinations. For our 3 elements, we multiply our choices. 2 times 2 times 2 equals 2 to the third equals 8 subsets. For the general formula, if we have a set with n elements, we simply make that two-way choice n times. That gives us 2 times 2 times 2 times ... 2 equals 2 to the power of n. Now, let's actually systematically construct the 8 subsets. We can perfectly map our 8 combinations using binary math. Let 1 mean in and 0 mean out. If we choose 0 for A, 0 for B, and 0 for C, our bag is empty. The resulting subset is empty. If we choose 1 for A, 1 for B, and 1 for C, we took everything. The subset is A, B, C. This table translates every combination of 1s and 0s into a physical subset. How do we draw this table on paper without messing up? We draw columns using powers of 2. The size of our alternating blocks of 0s and 1s is perfectly dictated by the powers of 2. For the rightmost column, 2 to the 0 equals 1, so we alternate every 1 row, 0, 1, 0, 1. For the next column, moving left, 2 to the 1 equals 2, so we alternate every 2 rows, 0, 0, 1, 1. For the next column, 2 to the 2 equals 4. We alternate every 4 rows, 0, 0, 0, 0, 1, 1, 1, 1. Now let's see the pattern in action for n equals 3, which gives us 8 rows. Let's look at the smaller 3-element table. Notice how the column patterns perfectly match 2 to the 2, 2 to the 1, and 2 to the 0, giving us neat blocks of 4, blocks of 2, and blocks of 1. Drawing down by powers of 2 is a magic trick that guarantees 0 duplicates and 0 skipped sets. Now we introduce a formal term, the power set, denoted as P of S. Now that our math has systematically constructed all 8 subsets without missing any, we can collect them into a single mathematical object. By definition, the collection of all subsets of a set S is called the power set of S. For our set S equals A, B, C, the power set contains all 8 pieces safely inside one big bracket, starting from the empty set, up to the full set, A, B, C. Now, let's level up to 4 elements. Now that we know the rules, let's level up to a 4-element set. What happens if we add just one more element to our back, making S equals A, B, C, D? Using the fundamental principle of counting, we make the in or out decision 4 separate times. This means we have 2 to the 4 equals 16 total subsets. Trying to list 16 combinations from your head guarantees mistakes. We must rely on the binary counting method we just learned. Here is the table systematically constructing all 16 subsets. By simply adding column D and following our binary pattern of alternating zeros and ones, we effortlessly and perfectly generate every single subset. We start with 4 zeros for the empty set, and end at the very bottom with 4 ones for the complete set, A, B, C, D. Finally, we can formally write the power set for all 4 elements. Now we can formally write the power set P of S. Notice how every single possible combination is perfectly accounted for. Our complete power set lists them all. We do a final cardinality check, and indeed, the cardinality of P of S is 16. We have mathematically proven our list is complete.